Okay, thanks for coming today's online seminar for Kia's hep-ph group. And so today we will have Dr. Yu Hamada from DESY talking about neutrino zeromodes on electroweak strings in light of topological insulators. So please start when you're ready.
Okay, thank you very much. So first of all, thank you very much for giving this nice opportunity, and yeah, it's a great pleasure to introduce our recent paper. So yeah, I'm Yu Hamada. I'm from DESY, and this talk is based on collaboration with these people: Eto-san, Jino-san, Nita-san, and Yamada-san. So they're Japanese people, and So in this talk, I will introduce two important but complicated concepts, which is electroweak string, or also known as a Z string, which is kind of a cosmic string-like object in the standard model. And another concept is a topological invariant, which is often used in condensed matter physics to characterize some topological nature of the material. And yeah, I will explain the electroweak string first. Afterwards, I will explain some topological nature of them. So first of all, let me start with some brief explanation about soliton. So what is soliton? So as you know, when we start to study some quantum field theory, for example, by Peskincher textbook, then we may know that a particle is described by some perturbative excitation and vacuum. So for example, when we have some annihilation and creation operator, then let's act the creation operator on the vacuum, then we get some perturbative excitation, which corresponds to the particle. On the other hand, soliton is different from particle. The soliton is classical and coherent excitation. So this is kind of non-perturbative and but big excitation. And in some sense, this can be regarded as some condensation of particles, or like a lump of a lot of many particles. And one famous example of soliton is tsunami, so which is something like this picture. Actually, this picture is not tsunami, but something like this one. And the tsunami is not perturbative, right? So it's a big wave and a very very coherent big wave instead of perturbative excitation. So this is well-known example. And so then you may think that soliton is a kind of special object and it's rare in a usual theories. But actually, it's not so special. Instead, it's a kind of ubiquitous in the quantum field theories. So let me briefly review one simple famous example of soliton, which is called Abrikosov-Nielsen-Olsen string, or ANO string in short. So let's consider the following 3 plus 1 dimensional Higgs model, whose Lagrangian is described by this one. So here we have U1 gauge field here, and U1 complex scalar field phi. And this has some potential, like this, Mexican hat or like a wine bottle type potential here. Then this complex scalar phi takes a wave, and this spontaneously breaks the U1 gauge symmetry. And in this model, let's consider the following configuration in the polar coordinate. So here, polar coordinate is given by this one. So R corresponds to the radial coordinate in the XY space, and theta corresponds to the rotational angle around the z-axis. Then let's consider the following configuration. So F is given by this one. So here V is some wave, and F of R is some function of R, and exponential I theta. And also we have a gauge field like this. So A of R is some function of R. And in this configuration, we can see that the phase of phi is given by exponential I theta. This has a winding number unity. That is, when so the phase of phi is identified with a spatial angle theta around the z-axis. So this means that if we change the spatial angle theta from 0 to pi, let's say, then the phase of phi also changes from 0 to 2 pi. So there is a one-to-one correspondence between the spatial angle theta and the phase of complex scalar phi. So this is called, this has one number unity. And substituting this configuration into the equation of motion, we can solve the equations and then we get some solutions of them. So then the solutions of the F and A shown here, then we can see that the F goes to 0 around R equal to 0. So this means that R equal to 0 corresponds to the z-axis. So this means that there is some finite energy excitation along the z-axis. So that's why this is called string. So this is a string-like object along z-axis.
Sorry, can I ask something?
Yeah,
Do
sure.
you hear me? Yeah. Now I'm trying to understand your explanation. Here now you're rewriting the scalar field phi with respect to the polar coordinates, right? Polar coordinates.
Yeah.
Here, where
Yeah.
is t? Where is time?
T means time.
Yeah. Now you're writing
Sorry.
the
Yeah. So
yeah.
this. So now I'm considering static configuration, which doesn't depend on time.
Statics. Static configuration.
Yeah.
I see. And
Yeah.
then yeah.
So
Then
in that sense, this object doesn't move in at this stage.
yeah. And then
Yeah.
in general, if we write down the complex field, then also in the phase part, the theta has to depends on x, y, z, right? In general, if we consider
So
if we
it's
consider if we consider the general case, then we usually write down the real part, and then for the imaginary part, we just write down the exponential I Goldstone version part.
okay.
Yeah. Then in general, even in the exponent, there is another field which depends on position, right? But in this case, the theta is just the angle in the position space.
Right.
So yeah. So my question is, now you are considering a kind of a special configuration of field, or
Well, yes.
yeah.
So now, I'm just concentrating on some static configuration that which doesn't depend on t or also doesn't depend on z. And so we are looking for static configuration. Afterwards, we can, for example, consider some motion of the object. Then the configuration does depend on the t and z and so on.
I see. And then would you please explain once more about why we call this as a string? I want to understand
Okay.
yeah.
Yeah, so this F and A are a
Yeah.
function of R. So R is a distance from the z-axis.
Yes.
And so that means R, large R corresponds to the far from the z-axis. On the other hand, R is 0 correspond to the on the z-axis.
Yes.
And if we see the large R region, which gives F and A go to the 1, that means this goes to vacuum value. On the other hand, if we go to R equal to 0, then this means that F goes to 0. This means that phi is 0. And of course, phi 0 is not a vacuum, so it's a excitation. So that means if we look along the z-axis, then we can see some finite energy excitation along the z-axis. So it looks like a string object.
Just you mean now we can consider the field phi as a g-axis value.
sorry, the
Yeah,
axis
because
what?
g-axis value. Yeah, just we can consider the field phi value as a g-axis value, isn't it? Because in your field configuration there is no g-axis value, so just since the
So what do you mean by the axis value?
yeah, just if we consider two variable function, then
Uh-huh.
we can say the function value as a g-axis. We can think like that, right?
Mm-hmm.
Yeah, naively. In general, if we consider two value function, then the function can be dealt with as a g-axis value. That's what I mean.
So you mean f overall depends on z or something like that?
No. Now you're considering R value is just
Yeah.
depending on x and y coordinates, right?
Right.
Yeah.
Right.
Yeah. So if just as long as if we choose the x and y value, then the
Uh-huh.
phi value is determined. That's what you mean, right?
Right.
Yeah.
Then
So
doesn't depend on z and t.
yeah, in that sense, now what I'm wondering is the left-hand side, the phi is
Uh-huh.
can be kind of dealt with as a kind of a g value.
I think this is something like a cylindrical symmetric configuration.
Yeah.
Okay. Please go ahead. Let me ask you later. Yeah.
Okay, thank you.
Yeah.
So,
Thank you.
so
Thank you.
yes,
Yeah.
sorry. So can I have two naive questions?
Yeah,
Um,
sure.
yeah, the first one is that here the trivial phase evolution is suppressed, right? E to the power of minus
Real.
imt.
Sorry, can I say again?
So the trivial phase evolution, IMT term,
Mm-hmm.
exponential IMT is suppressed, right?
Yeah, I don't consider that
Okay,
time
yeah, sure.
evolution. Yeah.
Okay, sure. And the next question is, how is the dimension of the spatial dimension of the soliton is determined? Is it depends on the field dimension of the field space?
Yeah. Dimension means this
Right.
one-dimensional
So
object or
yeah,
something like that.
one-dimensional string or zero-dimensional just a solitonic object or two-dimensional walls.
Okay, that's a very nice question. So for example, in this case, we have a U1 symmetry, and then we can
Mhm.
consider this string-like object.
Right. Yeah. Right.
Actually, this depends on the symmetry, or let's say the structure of the vacuum.
Okay.
And for example, another example is a tooth polyakov monopole, which is a point-like object, right? And it's a
Right.
zero
Yeah.
dimension.
Mhm.
And in such a case, the stability is from the SU2 symmetry broken down to U1. So which means the vacuum is S2 instead of S1 here.
I see. Okay. I see.
So yeah.
Okay.
Yeah, thank you. It's actually this is very important point. So this string-like object is topologically stable, and this is because some in a mathematical language, this is because pi1, which is the first homotopy group of U1, is equal to z, just an integer. So this means that so there exists one-to-one correspondence between S1 and to U1. So here, this S1 corresponds to this circle on the XY space, and this U1 corresponds to this circle on the which is bottom of the potential, or let's say this vacuum manifold. And we can consider, some non-trivial map between this S1 and the U1. For example, in this case, this is completely one-to-one correspondence between the S1 and U1. And this is the case of this configuration, for example. On the other hand, we can consider more complicated one. For example, this S1 corresponds to this U1 twice. For example, so if we change from 0 to 2 pi on this circle, then the angle of U1 changes twice from to 2 pi and to 4 pi and so on. So this means that we can consider some winding number between S1 and U1, and this ensures the topological stability of this configuration. So that means, so this, as I said, this has a winding number 1, but the vacuum doesn't have winding number. It's just a winding number 0. So that means the winding number 1 configuration cannot be continuously deformed into the vacuum. So this ensures the topological stability of this object. And so this object, so this object is often called vortex string. And this vortex string is very ubiquitous in modern physics. For example, if we consider some magnetic flux tube in superconducting material, then this magnetic flux tube is described by the NO vortex string. So this is a picture of the superconductor, and if we apply the strong magnetic field, then this can penetrate into the penetrate into the superconductor, and this tube is nothing but the vortex string. And also we can consider such an object in the universe, which is called cosmic string. And the cosmic string sometimes affect the CMB fluctuation, or this can be observed by gravitational wave in principle. And this is a strong evidence of new physics, but they haven't yet been discovered so far. And on the other hand, in the astrophysical context, there is a superfluid vortex in neutron star. This is also an example of some vortex string. Then, so you may think that can we consider some similar object in the standard model, because standard model is in some sense superconducting state, superconducting material. So SU2 times U1 symmetry is broken into U1 element symmetry. So it's a kind of superconducting object. Then, so the problem is that if we can consider the similar object in the standard model. So naively, we can consider such object by embedding the NO vortex into the U1Z part in the SU2 times U1 symmetry. So of course, so let's consider the Higgs doublet with some covariant derivative. So here, covariant derivative is of course given by this 2x2 matrix from the 2x2 Pauli matrices and some U1 hyperjudged diagonal part, and we can rewrite this covariant derivative here, and actually we can consider some embedding of the NO vortex into this U1Z part. That means we can consider some winding configuration on this lower component of the Higgs doublet, and let's embed the gauge field configuration into this Z gauge boson here, like this. And then the other fields are set to 0. So this is a naive embedding of the NO vortex in this U1Z part in the standard model. And this configuration has a finite Z boson flux tube. For example, if you integrate the magnetic flux of Z boson on the XY plane, then you get some finite value of the flux tube corresponding to Z boson. So that's why this is called. This object is called a Z string or Z string, and this is also known as a electroweak string. However, this Z string is unstable in the standard model. So actually, there are a lot of studies so far, and actually this was very hot topic in the 90s, but nowadays not so popular. But anyway, so there are a lot of study about the stability of the Z string, and it is known that this can be stable in this region. So here the horizontal axis corresponds to the Weinberg angle of the standard model, and this vertical axis corresponds to the ratio between the standard model Higgs boson and the Z boson. And this study says that in this region, this Z string can be stable. However, of course, the we know that's the correct Weinberg angle on the Higgs boson mass and Z boson mass, and actually the measured physical point is here. So this is far from the stable region. So this means that in the realistic model parameters in the standard model, Z boson is not stable. It's unstable, unfortunately. And this is actually easy to understand because in the standard model, the symmetry breaking structure is SU2 times U1 into the U1 element. So that means the vacuum of the standard model is given by S3, three-dimensional sphere. And in such a case, we cannot consider any topological invariant because even when we consider some winding number or winding on the S3, but this winding can be removed by continuous deformation. So that means there is no efficient topological invariant in the standard model. So that's why this string is not stable.
Can I have a question?
Yeah, sure.
So I naively expect just varying those parameters like the theta W or the ratio between the Higgs and the Z boson does not change the vacuum structure from this 3 to
that's
something.
a very good point.
Then why there's a stable region there?
Yeah, that's a very nice point. Nice question. Okay, let's consider the Weinberg sine theta is equal to 1. This means that the Weinberg angle is pi over 2. That means, Weinberg angle, let's say. Yeah, so that means SU2 gauge coupling constant is completely 0.
Okay.
So that means the gauge symmetry is just U1 hypercharge, U1 hyper, and SU2 is just a global symmetry.
Oh.
And so we can say approximately U1 gauge symmetry is broken by the Higgs field. Of course, if U1 hypercharge, U1 hyper is broken.
Okay.
But of course, there is a SU2 global symmetry, so it's a not trivial point. But in this region, the existence of the U1, the existence of SU2 global symmetry is not so significant.
I see.
In this region. That means we can ignore the global SU2 symmetry, and approximately there is only U1 hyper gauge field. U1 hyper gauge symmetry, which is broken into the U1 element. It's U1 element comes from the SU2, but anyway, sorry. U1 hyper is spontaneously broken by the Higgs doublet.
I see.
Yeah. Yeah, but anyway, it's a kind of special region. I mean, exceptional region. So in general, this cannot be stable.
Okay.
Yeah. But how? So, but let's consider some fermions in the standard model. For example, in the standard model there are a lot of fermions. And of course, the Higgs doublet and Z gauge field couples to the standard model fermions. So in that sense, this Z string also couples to the fermions. And what happens in the when we consider such a coupling? So let's solve the Dirac equation in the background of the Z string, which means that we have to solve this Dirac equation. Let's say let's concentrate on the lepton sector in the standard model. So let's say ignore the quark sector. Then we get the left-hand neutrinos and the left-hand electron, and we also have right-hand electrons for one generation. Then actually solving these Dirac equations, we get the fermion zero mode, or also known as a massless modes, which is localized on the Z string. So this is something like Kawasaki zero mode. So when we consider some extra dimension, and when we solve some equation motion, then we get some localized mode on the lower dimensions. So this is very similar. So even when consider the 3+1 dimensions, but after obtaining some zero mode solutions, we get some localized solution, which is around this one-dimensional object. And in the end, we can see that for example, in the lepton sector, this left-handed neutrino gives a right mover mode along the z-axis, along the z string. On the other hand, this electrons gives one left mover on the z string. So in that sense, if we consider 1+1 dimensional Dirac spectrum, the Dirac spectrum is given by this one. So this Pz corresponds to the z directions momentum, and omega is the energy eigenvalue. And we can see that this, we have two massless right mover and left mover in a two-dimensional system. But such a pair of the zero modes easily disappear by continuous deformation, because if we deform the z-string object, then this pair of the massless modes easily get some finite mass, like this red one. So that means this massless modes easily disappeared after performing some continuous deformation of the string. But actually, some people conjectured that this situation can change drastically when we consider other models. So for example, in some models with the extended neutrino sector, for example, type 1 seesaw model or type 2 seesaw model, then neutrino zero mode may not appear on the Z string. That means on this part, this line doesn't exist in the some extended model. Then that means we only have one left mover, which is from the electrons. And this single zero mode from electron cannot be removed by any continuous deformation, because even when we deform some Z-string configuration, then we cannot have this one, right? So we cannot have this spectrum on the two dimensions. So that means we cannot remove this one single zero mode from electrons.
Sorry.
Well, in other words, yeah, sure.
Oh, so the deformation means the deformation in the space. I mean, the spatial shape is deformed, right?
Yes, exactly, yeah.
And so in the previous slides, that when the Z string is spatially deformed, then these zero modes are disappears. That's what you're saying, right?
Yeah, right.
So that these zero modes are not propagating along the string. It is not bounded for the string, right?
Well, actually, it depends on the mode. I mean, it depends on how you deform the strings. I mean, sometimes this is still localized, and sometimes this is escaping to the bulk.
Okay, so
I mean,
yeah, so
yeah, so this corresponds to the yeah, please go ahead.
Oh yeah. So my real question is, in the Dirac equation you showed in the above. So when the string deforms, which part is altered and the zero modes disappear?
Sorry, which part means which part of the Dirac equation?
Yeah.
Okay. So let me see. For example, if we deform the string, then we cannot have a polar coordinate, right? So this equation would be very complicated.
Okay.
Yeah. So maybe we cannot have this simple equation.
I see.
And yeah. Or even when we keep the axial symmetry, then we can have some deformation, like this breathing, a bit expanding or a bit shrinking of the string, for example. Then we can have but in that case there's no disappearance of the zero mode. Or let me see. Or okay, maybe I should explain this. Or let's say we can turn on the upper component of the Higgs doublet here. For example, this string corresponds to only this part, and in this case, this is 0, but we can turn on this part. And this gives a coupling between the electron and the neutrino, and this may give some non-trivial mass term between the two zeromodes. This also another case to give a mass. Yeah.
And then if the neutrino does not appear in this diagram, then it cannot happen.
Exactly. Yeah.
Okay.
Yeah, I have a related question.
Yeah, sure.
In this single zero mode case, why can't it get mass? Or
okay, so because there's no counterpartner of this zero mode. So in some sense, this two-dimensional theory is effectively described by the one Y fermion. So we can write down mass.
Okay, I see.
Yeah.
Okay, thanks.
Yeah, thank you very much. Sorry. So that means okay. So these people conjectured that this can happen. This situation may happen in some extended models like type 1 or type 2 seesaw, whatever. And they conjectured that if this is true, if there is only one single zero mode, then this string might be stabilized, might be topologically stabilized, because this means that there is some non-trivial, this situation cannot be deformed into the vacuum by any continuous deformation. So this implies that there is some topological invariant behind this object. So in other words, they conjectured some new topological invariant in this model, in this theory, and this can topologically stabilize the Z string. But our motivation is the following. So we want to examine if this mechanism works. So we want to check. But actually, this is pretty hard usually. So because in order to do that, we have to count the number of the zero modes very carefully. But actually, the counting of number of the zero modes is sometimes very hard because the Dirac equation is usually can be solved by analytic procedure. So we have to solve the Dirac equation in a more convincing way, or like let's say some numerical technique and so on. But it easily misses some solutions. So the counting the zero mode in a correct way is pretty hard in in many cases. Then our proposal is the following. So let's use let's adopt a different way. So let's use the general topological invariant in the momentum space, which counts the number of the zero mode without solving the Dirac equation. And actually, such a topological invariant is often used in condensed matter physics. So we can import such a concept from the condensed matter physics. Then let's apply that concept to this model. Then our result is the following. So in the neutrino seesaw models, such as type 1, type 2 seesaw, or hybrids of the both models, then even in such models, the number of the zero mode is the same as the standard model. So in that sense, this mechanism doesn't work. So even when we consider such a model, these strings are still unstable, like the standard model. So this is our conclusion. So in the following, I will explain what is the topological invariant that we adopt. Afterwards, I will explain I will apply the topological invariant to some neutrino system models. Then we will see that still the number of the zero modes does not change, and the Z string is still unstable in such a models. Okay, so let me explain the topological invariant. And so topological invariant is sometimes very, convenient in the condensed matter physics. And let me give some, one well-known example of the topological invariant in the condensed matter physics. So this is called TKNN formula, named from these people, and this is, this is for quantum Hall effect in some, for the quantum Hall effect. And the quantum Hall effect means, some material, and when we apply the magnetic field and the electric field, then some current can flow on the edge of the material. So this is quantum Hall effect, and so yeah, let's consider some Hamiltonian of the material, and let this ket N and P be some energy eigenstate of the Hamiltonian, which is labeled with a band label N and Bloch momentum P. And from this ket, we can consider some Berry's connection, like this. So this P, so this part corresponds to the derivative with respect to P momentum. Then we get some Berry's connection. And in terms of these Berry's connections, we can define not define. So in this setup, let's consider some conductivity on the edge of this material. Then these people show that this conductivity is proportional to this quantity, which is given by these Berry's connections. And we can see that this quantity is nothing but the Chern number, and this is kind of a topological invariant defined in the momentum space. And actually, this is equal to the number of the edge modes defined in the momentum space. So this is not. So this is proportional to the number of the edge modes which is flowing on the edge of the material. And so this is very analogous to the topological invariant of the number of the magnetic monopole. For example, the number of the magnetic monopole is proportional to this quantity here, the magnetic flux of some surface integral surrounding the magnetic monopole, and we can see and we know that this is proportional to the quantized flux of the magnetic monopole. And actually, this is the same formula, same expression of this integration. So we can see that this is also topological invariant, and this corresponds to the number of the edge mode. But this is well known in the condensed matter physics. But let's consider alternative example of the topological invariant. So this topological invariant is given by these people, and so here this is very complicated expression. So this hat Z is a Green's functions of fermion in the string background. So this is, so for example, when we consider Z string on the Z axis, then this Green's function should be like this formula for this is just usual kinetic part, and this is some mass that has also XY dependence due to the existence of the string, and some non-trivial part, for example, gauge coupling, and so on. And because we have a translational invariance for T and Z directions, we can rewrite this T and Z with respect to the P3 and P0. This is just a Fourier transformation. On the other hand, there is no translational invariance to the X and Y direction because of the existence of the string. So this Green's function Z contains X and Y explicitly like this. And also this also this also has a a spatial derivative del x and del y. So this means that this Green's function is an operator acting on some xy functions. And so that's why we have a trace here. So this trace is a trace trace on the functional space of the xy functions. And also this integration corresponds to the integration controller on the P3, P4 plane, and this controller surrounds the origin on this two-dimensional plane. Then we get this topological invariance. So this is like a bit complicated calculation, but anyway, when we have a Green's function like this, then we can calculate this invariant.
Sorry, I have a question.
Yeah.
So in order that this quantity is topological, so naively the integrand has to be closed for. So is it correct? I mean, by taking the exterior derivative of the integrand, so it should vanish naively.
Yeah. Sorry, can I say again? If this has a closed form, this vanishes, right?
Yeah, if we take the exterior derivative of the integrand, so it should vanish, because otherwise, if we modify the circle C, it changes this quantity. So I just
right.
Yeah.
Right. Okay. So in the next, so let me explain it in the next page. Maybe.
Okay.
Yeah. So yeah, this expression is too complicated, and we cannot it's difficult to get some intuitive understanding from this expression. So let me rewrite this one in a more more understandable way. So so let's rewrite this Green's functions in terms of the P4. P4 comes from the weak rotation of the P0, and here H hat is a one particle Hamiltonian. And then let's take this trace which acts on the functional space, and so by inserting the energy eigenstates n blah n and ket n, then we can we can rewrite the trace in terms of the summation over the mode n. And here the ket n, here the z hat acts on n, and this is and let's define this as a zn. This is just a C number. This is not an operator. And the gn is given by this one. So here just this Hamiltonian is just replaced by this energy eigenvalue En. And also we can rewrite this expression by this one. So this just here we introduce by a complex variable P3 plus I P4 and so on. And so from this expression we can see that this integration picks up poles around the origin at which the Zn inverse should be 0. Otherwise, as Kawano-san says, otherwise this integration is completely 0, completely vanishes. But if this Green's function has some poles, then this gives some non-trivial value. And this means that only massless modes contribute to this integration. For example, if we consider massive mode, which means that the pole is not around the origin, so in that sense, this does give any contribution to this integration around the origin. So that means this only picks up massless poles. And when we consider massless poles, we can rewrite, we can consider this expression for the energy eigenvalue. So this energy eigenvalue depends on P3, which is z directions momentum, and let's just expand this energy eigenvalue as a function of P3, and let's denote the coefficient of the leading term of the P3 as lambda n, and let's forget about the higher order of the P3 because we are considering the around the origin. And this lambda n can be plus or minus, plus 1 or minus 1. And actually, this is nothing but the chirality of the massless mode in the two-dimensional sense. And substituting this expression in the Zn, then we have these integrations. And this means that this integration has a plus 1 when lambda n is plus, or this integration gives minus 1 if the lambda n is minus. So this is nothing but the number of the plus chirality minus number of the minus chirality. So this means this is nothing but the two-dimensional Dirac index. So that's why this is topological. So this is by any continuous deformation, this quantity doesn't change. So let's do some consistency check. So as is well known, when we couple some Dirac fermion with the NO vortex, then we have some localized zero modes along the NO string, NO vortex. So let's consider this coupling between the fermion here, Dirac fermion psi, and some complex scalar field phi. And let's consider this kind of NO vortex background. And we have this Green's function for this Dirac fermion like this, and substitute this Green's function into this complicated topological invariant. And actually, this calculation is pretty annoying. So let's skip the detail of the calculation. And in the end, we have plus 1. So this means that along the Z string, there is one massless mode from the Dirac fermion. And when we consider, n winding of NO string, let's say this is kind of a superposition of n NO vortex strings. Then we have n for the topological invariant. This means that n massless modes appear along the Z string, along the NO string. And actually, this is consistent with a well-known result. So this is the original paper by Jackie and Rossi, and they stated that when we consider n vortex background, we have n massless modes. So this is consistent with this result. So this means that our topological invariant successfully counts the number of the zero mode, which is coupled to which is appearing on the string. So far I explained the topological invariant, and then let's apply this invariant to other models, for example, type 1 seesaw models and so on.
Sorry.
So firstly, yeah.
Question. So is this topological number or topological quantity, so is it related to some anomaly in 3 dimension?
That's a very good point. Yeah, well, to be honest,
so this is nothing but
yeah.
Go
yeah,
ahead.
right. So to be honest, I only know about the simple cases, but anyway, so in simple cases, yeah, I think this is correspond to the anomaly inflow, I guess, and yeah, otherwise, if this is non-zero, that means the two-dimensional theory should be anomalous, and but of course, the full 3+1 dimensional theory is not anomalous. That means there is some anomaly inflow from the bulk.
Yeah, that's
And
naive.
yeah. And actually, in our paper, we write this quantity in a more this directly counts the number of the edge modes here, but we can rewrite this quantity in a more as a integration over the bulk space.
Okay.
Yeah, and I think that's integration of the over bulk space reduces some bulk anomaly in simple case. I think, but to be honest, in complicated, anyway, so yeah, in the standard model, the standard story is the following. So in the standard story is the if we count the edge mode on the some soliton or some lower dimensional system, and this has to match with the bulk anomaly, and both of them are given by some index theorem and so on. And in our case, this quantity is more general than index theorem, because we don't assume anything. We don't assume any gauge field, for example. We just assume some green function. So in that sense, this setup is more general than the case of the Dirac index theorem. But when we specify to some cases, then I think this reduces to such a usual anomaly inflow or such a standard setup, I guess.
Okay.
Yeah.
Thank you.
Yeah, thank you. So yeah, firstly, let me explain the type 2 seesaw model. So type 2 seesaw model is a popular and simple setup that consists of the standard model and some Higgs triplet field delta that has some hypercharge 2, and this delta is given is it's written by this formula, and A runs from 1 to 3, so we have delta 1, 2, and 3. So we have three complex field. And the Lagrangian is given by this one. Here, we have some non-trivial scalar potential of the standard model Higgs doublet and the Higgs triplet delta. And we also have a Yukawa coupling between the standard model lepton and this triplet field delta. And so in the broken phase, the standard model Higgs has some the usual vacuum expectation value. On the other hand, this delta also gets a non-zero vacuum expectation value on this component. And this wave gives a neutrino Majorana mass to the left-handed neutrino like this. And this gives a neutrino mass. And diagrammatically, this is expressed by this diagram. So we can see that this mass should be proportional to the mass of the delta, because this is mediated by delta. So we can see that if we take large heavier delta and a small wave, then we can naturally explain the light neutrino mass in this model. So then let's consider the Z string in this type 2 system model. So as I said before, Z string is a kind of embedding of the NO vortex to the U1 Z part in the electric symmetry. So the naive generalization is the following. So we have a phase corresponding to the U1Z here in the lower component of the Higgs doublet, and we also have the phase for this neutral component of the delta. And the important point is that because this delta has hypercharge 2, then this phase should be coefficient, it should have coefficient 2 here instead of 1. So this is because of the hypercharge 2. And then let's substitute this string background to the neutrino Lagrangian. And but this expression is a little bit annoying. So let's rewrite this expression by introducing NL. This is called Nambu-Golkov spinor. So this is 4-component spinor given by the new L and new LC, and this capital NL bar is given by this expression. Then we get this simple expression for the left-handed neutrino. And from this, we can write down the Green's function for the left-handed neutrino. Then we get this expression. And what is nice point is that formally, this expression is completely the same as the case of the Dirac fermion couples the NO string. But except for 2 in the phase coefficient here. So if we take if this is 1, then this is a completely same as the Dirac fermion. But now we have 2 here, but formally almost the same as the Dirac fermion. So then, performing the same calculation as the Dirac fermion case, then we can see that from these Green's functions, the topological invariant is given by this one. So here, this 2 comes from this 2 of the phase here, and this 1/2 comes from the following fact that the net degrees of freedom of this 4-component spinor is 2 instead of 4, because we start from the only new left-handed neutrino. So we have to multiply 1/2 here. Otherwise, this gives some overcounting for the degrees of freedom. So that's why the 1/2 should appear here. In the end, we have a 1 as a topological invariant. This means that there should be 1 Y fermion coming from the left-handed neutrino in this model. And actually, this is consistent with the explicit solutions of the Dirac equation. So actually, in our paper, we explicitly solve the Dirac equation for the left-handed neutrino in the Z-string background. Then we get these solutions, and this means that there is one, there is single Y fermion from this left-handed neutrino. So this should be this means that this topological invariant should be 1, and this is consistent with this argument without solving the Dirac equation. So this means that, as I said, the neutrino, left-handed neutrino, gives 1 single Y fermion in the background of Z string, and on the other hand, electron also gives a Y fermion, but actually its hierarchy is the opposite. So this means that the topological invariant from electron is -1, and actually this is completely the same as the argument of in the standard model, because electron doesn't couple to the Higgs spherical field. That means this only couples to the standard model Higgs and the Z boson. That means this part is completely the same as the standard model. So anyway, in the end, we have a +1 here and -1 here, and in total we have 0 for the topological invariant. So that means this is not the case. So we have both of the right mover from neutrino and the left mover from electron. So this means that there is no, they appear as a pair of the 2, Y fermions. And as I said in the introduction, they are easily, they easily disappear by some continuous deformation. In that sense, Z string can't be stabilized in this setup, so it is still unstable.
Sorry, is this electron left-handed or right-handed?
That's a good point. So actually, so left-handed electron and the right-handed electron, sorry, let's say this one while fermion comes from both of the left-handed and right-handed electron. Yeah, in that sense, this is kind of tricky. So left-handed and right-handed spinors gives one while fermion in the two-dimensional sense.
And it contributes -1, like right-handed.
Yeah, right. So it's it's a complicated in the so in that sense, we have to be careful about the right or the left-handed in which sense. And so, for example, this is one example of the one Dirac fermion couples to the NO vortex string, and this is just a usual Dirac fermion, and this is Dirac equation in the background of NO string, and this psi R and psi L is a right-handed or left-handed spinor in the four-dimensional sense. And after solving this Dirac equation, we have this zero-mode solution here. So we can see that these two components correspond to the two component spinors of the left-handed spinor, and this is also two component right-handed spinors. And we can see that the solution both of the left and right-handed spinors have non-zero component here, and this corresponds to the both of them describe one propagating mode along this for example left mover mode. In that sense, this is a in two-dimensional sense this is left mover mode, but this comes from the both of the left-handed and right-handed spinors in the four-dimensional sense.
Okay.
Yeah, thank you. So this is the case of the electron.
So in the two-dimensional language,
yeah,
is it right-handed? The combination of left and right in 4 dimension correspond to right-handed neutrino in 2 dimension. I'm not sure. Just
sorry, and are you saying about the neutrino zero mode or as electron?
So here you are saying that this left mover solution is coming from the combination of left and right.
Yeah, right.
In 4-dimensional space-time.
Yes.
But I guess, or I wonder, such a combination corresponds to right-handed neutrino, right-handed fermion, 2-dimensional sense. I'm just wondering. Yeah, maybe,
right.
we can discuss later.
So left mover or right, the hierarchy of the left mover or right mover in the two-dimensional sense depends on the actually isospin of the SU2 doublet.
Oh, sorry. Yeah, I think I misunderstood. Okay.
Sorry. So yeah, anyway, while fermion in the two-dimensional, while fermion in 2 dimensions comes from the both of the right-handed fermion and the left-handed fermion in the 4 dimensions in the usual case. And this is the case of the electron field. And in the neutrino case, this is more tricky because we have a Marana mass term without any Dirac mass term in the type 2 seesaw model. So in that sense, the neutrino in the type 2 seesaw is just exceptional case. And in this type 2 seesaw model, only left-handed neutrino gives one single, one while fermion in 2 dimensions. But this is exceptional. Does it make sense?
Yeah, thank you.
Okay, thank you. So yeah, anyway, so in a type 2 seesaw model, we have both of the right mover while fermion and the left mover while fermion and they are, so this implies that there's no non-trivial or topological quantity, and they can be easily, they can easily disappear, and this string is still unstable. And let's do the same thing in type 1 system model. And we have we have standard model fields and the right-hand neutrino here, and the Lagrangian is given by this one. So here, this is a kinetic term for the right-hand neutrino, and we have a right-hand neutrino mass, Majorana mass, and we have a Dirac type Yukawa between the left-hand neutrino and the right-hand neutrino here, and this phi is a standard model Higgs doublet. And due to the existence of this Majorana mass term, we can have a Majorana neutrino mass for the active neutrino. Then we can see that this neutrino mass is inversely proportional to the heavy Majorana mass term. Heavy Majorana mass, that means when the Majorana mass is heavy, then we can explain the light neutrino mass. And this is very nice for for example, leptogenesis or Estot-Ten-Gat. And one of the lightest stellar neutrino may become the candidate of the dark matter, for example. And so in that sense, this is a very nice setup for the in the phenomenological sense. And let's again consider the Z string in this setup. So again, so in this case, we only have the one Higgs doublet without any other scalar fields. So we can again consider the Z string configuration is the same as before. We only have just a phase rotation for the neutral Higgs component here, and substituting this configuration into the neutrino Lagrangian, then we can have this mass term for the neutrino. And we can see that this 2x2 mass matrix has one zero component here, and the other components are non-zero. And this component corresponds to the left-hand Majorana mass, and this component corresponds to the right-hand Majorana mass. And in this case, this is zero. And we also have a Dirac mass here between the left and the right neutrinos. And we can see that this determinant is given by this equation, because this product is zero, and we only have these directions, and this is given by this one. And because the topological invariant n is topological, it is invariant as long as this determinant is non-zero. So this is the same as the argument in the for example in the condensed matter physics. So topological invariant doesn't change even when we deform the setup continuously. So in that sense, we can change the parameter such as mass parameter in the setup in the model as long as this mass determinant is zero. Determinant becomes zero. And we see that we know that this determinant is given by this one. So this doesn't depend on the Majorana mass here. So that means we can turn off the Majorana mass here. And actually, this doesn't change the topological invariant. So let's turn off here. Then we can see that this setup is the same as the Dirac case, because there is no Majorana mass here. So this is just Dirac mass. So this is completely the same as the Dirac fermion coupled to the string background. In the end, we have the same quantity as the Dirac fermion. So this is just topological invariant is just one. This means that the single wire fermion from the Dirac fermion. And actually, this is also consistent with the previous works given by these people. So this is, yeah. So, but we don't have to solve any Dirac equation. So we know that this is topological, so we can turn off the right antimatter mass. So we see that this is the same as Dirac case without solving the Dirac equation. And then, so for next, let's consider a more complicated setup, which is a hybrid model of the type 1, type 2 seesaw models. So in this model, we have a standard model fields and the right anti-neutrino and Higgs turpet field delta. And then the Lagrangian is a little bit complicated. So here, this is the kinetic term for the Higgs turpet and some scale potential. And we have a Yukawa coupling between the standard model lepton delta and the right-hand neutrino mass term and Dirac Yukawa. And then again, in this case, the standard model Higgs has some wave, and this turpet also has some wave. And of course, this is not an elegant solution for the neutrino mass because this is just complicated. But let's consider this model because we are interested in whether the Z string is stabilized or not. So let's check that. Let's check if the Z string is stabilized in this complicated model. But again, we have a standard model Higgs doublet and the turpet. So the Z string configuration is given by this one. So the winding phase of the neutral Higgs and the winding phase of the neutral component of the delta. And again, this is proportional to 2 because the turpet has a hypercharge 2. And in this case, we have this 2x2 neutrino mass matrix. And in this case, this is most general because we have a left-hand Hamada mass, right-hand Hamada mass, and Dirac masses. And this mass matrix, the determinant of this mass matrix is given by this one here. And we can see that this model is divided into the 2 topological phases. One is just this quantity is positive or this quantity is negative. And let's call this case as a type 2 like case, and let's call this case as a type 1 like case. And as I said before, the topological invariant N is topological, so it doesn't change even when we turn off some mass parameters. So let's turn off the Dirac mass here, but this doesn't change the sign of this determinant. So this, we keep this quantity non-zero. Then after turning off the Dirac mass, then we can see that this is completely the same as the type 2 case because when these components are 0, that means the right-hand neutrino are completely decoupled. So that means we only have left-hand Hamada mass here. So this is the same as the type 2 seesaw model. On the other hand, in this case, we can turn off the Hamada mass ML and MR here, and this keep this quantity non-zero. And in such a case, we don't have this term and this term, this part and this part, and this is completely the same as the Dirac fermion case, and this is the same as type 1 seesaw case. So we can see that in both cases, the topological invariant is equal to 1. That means this gives a single wild fermion in the background of the Z string. So so far I have considered some extended models, type 1, type 2, and the hybrid. But so far, in all cases, the number of the neutrino zero mode is 1. That means the topological invariant N is equal to 1. And as I said before, we also have an electron here, which couples the standard model Higgs and the Z boson. Then the total topological invariant is the sum of the neutrino and the electron. And as I said, the neutrino gives 1 plus 1 here, and the electron gives -1 here. And in total, this is 0 in all models, all cases. In the end, in all cases, this is not the case. Instead, we have both of the wire fermions from neutrino and the wire fermion from the electrons. In that sense, there is no non-zero Dirac non-zero Dirac index in these models. So in the end, we found that this Z-string is still unstable even when we consider extended models. So this is a summary of my talk. So so some people conjectured that when we consider some number of the zeromodes appearing on the Z-string, this may play some important roles to stabilize the Z-string. And especially when we consider the neutrino system models like type 1, type 2, and so on, then this might change the number of the zero mode of the neutrino. And this can be different from those of the standard model. But so in this talk, we have used some topological invariant defined in the momentum space and shown that all system models, type 1, type 2, and the hybrid gives the topological invariant 1 from the neutrino sector. And combining with the electrons, the total number of the zero mode is just 0. So this means that this means that this is the same as the standard model, and the Z-string is still unstable in those models. This is our conclusion. Yeah, that's it. Thank you very much.
Okay, thank you very much for the nice talk. So, are there any questions or comments?
Maybe some people are raising their hand.
Oh, really?
Can I have some live question? So you made a comments on about the stability of string related to the symmetry or the symmetry not only not only for the number of zero modes, right? So can we make some similar comment when we include this seesaw model? You already discussed about the number of degrees of freedom, right?
Okay, I see. That's a very, very good point. So, okay, yeah. So, yeah. So, for example, in the type 2 seesaw model, we have a Higgs doublet and Higgs triplet, and let me see. Yeah, still in this case, in this model, still we have a vacuum manifold F3, which means that there is no topological invariant that's stabilizing the Z-string. So in that sense, this is not enough. So symmetry is not enough to stabilize the Z-string. And also in the type 1 seesaw model, that's the same. So because we only have a Higgs doublet field here, and the symmetry breaking is completely the same as the standard model. So also in this model, there's no this cannot stabilize the Z-string. But one exceptional case is that if we turn off this term in the type 2 seesaw model, then this gives some accidental symmetry, accidental global symmetry, which is a U1 lepton number. And this can give some topologically stable object. But in that case, this is not the Z-string. So this is just coming from the U1 lepton number. So in that sense, this is no stable Z-string, or even in that case.
I see. Great, thank you.
Yeah, thank you.
So, Kiyoharu, do you have questions?
Yeah, actually, so you already answered my question about this
Mhm.
mutant. So I just wonder, so do you have any idea of realizing stable Z string? So you said one possibility is putting this mutant 0.
Mhm. Yeah,
So
that's one option, but you know, I think such a case is not allowed in the phenomenological sense, because this gives
Yeah.
some spontaneous breaking of the U1 lepton, which means but it could be like a myron, but anyway, I think this is not allowed, because if you turn off this part, then this means that we cannot write down, we cannot have a myron mass.
right.
I mean, we cannot have a neutrino mass here. So in that sense, we cannot turn off here. And for other options, actually there are several proposals to stabilize the Z string before, and to be honest, all of the proposals do not work. And to my knowledge, there is no way to stabilize Z string.
You mean based on your analysis, they don't work?
Yeah, I mean, besides the fermion zeromodes, for example, some people propose that this Z string can be stabilized by the final temperature effect.
Uh-huh.
For example, in the early universe, and they give some arguments, and they showed, for example, they naively showed something about the stability, but to be honest, their arguments can't be justified, and the Z string can't be still can't be stabilized.
Mm.
And yeah, actually that's our in this collaboration we started to stabilize the Z string in some mechanism, but actually we couldn't find any mechanism to stabilize the Z string. So to my knowledge, I think it's I think there's no no mechanism
I
to
see.
stabilize Z string. Yeah.
Okay, thank you.
Yeah, thank you.
So are there any questions or comments? If not, let's thank the speaker again.
Thank you very much.
Yeah, thank you very much for giving a nice talk.